Everybody. So good afternoon, everyone. Welcome to this session of the NETEX colloquium. My name is Francesco Petruccione, and I'm the interim director of NETEX. Today, it's a pleasure again to introduce Professor Nico Orce. Nico is a nuclear physicist based at the University of the Western Cape, but he's also a visiting professor at the University of York. Yeah? And if you read his bio, you will see that he was active in all big nuclear physics activities, yeah? From the Mandela Lab to Itemba Lab, SALT, MNL, Triumph, CERN, and so on and so forth. Yeah? He's also the leading investigator and the spokesperson for the I don't know if you pronounce it GAMCA or GMKA spectrometer. Yeah,
GAMCA is the meaning of
GAMCA. Okay, perfect. And he's also the chair of the Taste of Nuclear Physics, and he's a referee for many journals, and is really promoting theoretical and computational science in South Africa. And we really appreciate his effort to help us make NETEX a success. So Nico, thank you very much for being with us. You're most welcome to start sharing your screen and start your presentation. And, and to the participants, please make use of the Q&A facility. And since we're not so many, you're also welcome to raise your hand, and we will make a plan to give you the right to ask your question in person. Nico, thank you very much.
Thank you, Francesco and Ilya, for your support, and also Rene. So today I'm going to talk about something very special because there are lots of work trying to understand from the beginning of times why, how the elements are created in our universe, and why we have these particular abundances of elements around us. So everything, I will say, started like about 20 years ago. This presentation started 20 years ago when I went to Oxford to give a talk, and someone in the audience asked me, what's happening with this? I remember studying nuclear physics, and I remember this semi-empirical mass formula, and do you still use it, or are you using it by any means? You know, I thought it was interesting. I thought for a second, I said, well, I don't know. I don't think so. You know, this seems to be like a very old formula that no one is using nowadays. I didn't understand at that time. I didn't know at that time that the symmetry energy was so important in trying to understand neutron stars and the cores of supernova. And you know, there were actually conferences dedicated to the symmetry energy and to the semi-empirical mass formula in a way. So I didn't understand that this relative abundance of elements actually depended on the symmetry energy until recently. So in fact, that's one of the 11 greatest unanswered questions, as the journal Discover stated. Question 3, how were the elements from iron to uranium made, right? And this is the title of this talk on the universality of the art process. We'll explain what the art process means. It's the rapid neutron capture process. And finally, in that day in Oxford, I ended up in this little hall here. Actually, it looks very beautiful. It's close to that dome in Oxford. And we got lost in this cathedral or whatever. And then suddenly we met one of those priests, very big guy, big block, you know, dressed with the typical church clothes. And he asked me very deeply and heavenly, are you coming to the ceremony? And I say, yeah, I'm coming to the ceremony. So I ended up sitting up in this chair here, and he was sitting close to me, besides me, and they gave us some pamphlets, and I started singing with the Oxford choir. But that's another story I will tell you another day, the day I sang for the Oxford choir, how there was that was a real story. It was actually in this hole, in this particular hole, I remember very well. So now, about the abundance of chemical elements. It was Victor Weisskopf who wrote these beautiful paragraph about the abundance of elements. The composition of matter, as we see today, is the product of nuclear reactions, which have taken place a long time ago in the stars or in star explosions, where conditions prevail, which we simulate in a very microscopic way within our accelerating machines. Hence, the material basis of the world in which we live is a product of the laws of nuclear physics. I cannot better illustrate the interconnection of all facts of nature than by pointing to the chart of abundances of elements. Each maximum, each minimum in the curve of abundances corresponds to some trait of nuclear dynamics, here a closed shell, there a strong neutron cross-section, or a low binding energy. So this pattern here is all a result of different nuclear reactions. But let's go back in a little bit in time. Let's go back to those wrinkles in time that Martin Bucher is presenting to us beautifully in the school, and we see that the W map, suddenly changed a little bit the landscape of what we believe in the following way. Suddenly we realize that only like 4% of all matter was only that visible matter that we see around us. Everything that makes us alive, make us rich, or make us poor, everything, that 4% of everything was just atoms, right? 4 or 5%. 23% was dark matter, according to the gravitation that cannot be explained outside the center of the galaxies, how stars move faster than they should. And also that dark energy is the remaining, which will explain the expansion of the universe as we see it today. So that was before 13.7 billion years ago, when the Big Bang, and then dark matter was converted into this expansion of the universe, the inflation at some point, and this is what we understand now. And we are not interested in that, obviously. We're interested in another little percentage. Within that 4%, we know that there is another 74%, which is hydrogen, a similar percentage to dark energy, dark matter and visible matter. Is curiously, there's probably not related, but as a curiosity, 74% is hydrogen, 24% is helium, and the rest, as you can see, is a little bit of oxygen, carbon, neon, iron, nitrogen, and those elements that we are interested in this talk today, they are only less than 0.05% of elements heavier than iron within that 4%, right? We see this pattern of abundances in our universe, in the sun's photosphere, even in Jupiter, in different places where the conditions remain for hydrogen and helium to domain, right? As in this case, we see the abundances on Earth. There's a nice picture of a periodic table, which is wrong. It's a nice picture showing the abundances, the relative abundances, but in reality, this is the more a much better picture, where we have lots of silicon, oxygen, aluminum, iron, some of sodium, magnesium, potassium, and calcium, right? So gas planets, obviously, they have different abundances, and this is because in those innermost planets, the solar heat during the planet formation was very high and drove most volatile compounds into space, those hydrocarbons, for instance, except oxygen, which is found in silicate materials, silicate oxide, which is like 90% of the Earth's crust, right? So we lost most of the unlike Jupiter and other gaseous planets, we lost most of the hydrogen and the helium, and so we have lots of silicon instead. But still, the abundances remain the same in Jupiter as for the Sun, as for the rest of the universe as we see it today. So this is our periodic table, and this is what we know from Dmitry Mendeleev. This is a beautiful painting which is in the Tretiakov gallery in Moscow, which I was there a few years back, 6 years ago actually. And there's a beautiful painting of Dmitry Mendeleev, who was very bold, even predicted new elements according to the universal pattern of elements in the periodic table. And he could predict and he could correct certain scientists who didn't believe what he was predicting. But obviously, when you have a pattern and that pattern has a logic, there's nothing you can do against that. So what we are interested today is not in the hydrogen and helium, which they were produced in the Big Bang, but those elements who are produced above iron, all the rest that we see, the gold, the platinum, the palladium, the silver, all the heavy elements above iron, where we don't know where they actually, how they were produced precisely. So, as you know, this is the binding energy curve per nucleon. And you have the light nuclei that they fused and they keep fusing. And then there's a interplay between gravity and nuclear reactions. Gravity keeps pulling things down, and nuclear reactions keeps emitting energy outwards, right? And then while we are burning hydrogen, as we are burning hydrogen right now, our sun keeps shining. At some point, all the hydrogen will disappear, all the fuel will disappear, and then gravity will win, and then gravity will pull all that matter down, and then suddenly, until you reach certain temperatures for the hydrogen to burn, and then again there will be a much bigger sun, and there's a cycle so far until reaching, depending on the masses, reaching iron, and this is the end point. Iron is the end point where you can get some energy, because the energy release is exothermic, is positive Q value, and from this point onwards, actually is nickel 62, the most tightly bound nucleus, nickel 62. After nickel 62, everything is going down according to Einstein's formula. EMC squared, the binding energy will be, the Q value will be negative from here, and then the other process, which will be have a positive Q value, will be the fission. So fusion goes up to here, and the rest of the elements are produced by neutron capture, where there's no Coulomb barrier involved, right? And this is how you produce these elements. What we are interested in is in above this line, this blue line, iron here, how these elements are produced. So, as Weisskopf mentioned, there's a lot of nuclear reactions happening, and depending on the rates, something will favor beta-decay or proton capture or alpha capture, and depending also on the seeds, nuclei, and the source of particles, of alpha particles versus proton or helium-3 or whatever it is in that environment, we have the process, these scatter processes, which depends on those reaction rates, right? And it seems quite complicated, but this is how we evolve and we move on, and also depends on the temperatures, right? So we move on that path, on that nuclear landscape via nuclear reactions. So then all these paths, or this network of creation of elements happens in different explosive scenarios where the temperatures are big enough for this some point fusion to be created, to have enough energy to overcome the Coulomb barrier together with quantum tunneling. And at some point also we will need lots of neutrons for those elements around here to be produced, and there will be a competition between you capture one neutron and eventually β-decay will win the game between the two processes. Either you capture one neutron or you β-decay, and this is how these elements, the value of stability, they are produced, and each one has a particular abundance. Each isotope, it has a particular abundance depending on those nuclear reactions, on that nuclear structure, and those binding energies. So different, as I say, different explosive scenarios are the nurseries of elements. And one of those is the S process, or the slow neutron capture process, where it happens quite regularly, and there's a flux of 10 to the 5, 10 to the 6 neutrons per cube centimeter. And this is one of the main reactions which produce those neutrons. As I said before, you neutron capture here, and eventually you either β-decay, normally a beta minus decay because you're on the neutron rich side. So this is what happens, and this is how we see that, for instance, you follow a path close to the value of stability. All these black squares of these black nuclei are stable nuclei, stable isotopes, and you will gain one neutron, one neutron, one neutron, one neutron, and you go here to the unstable one, and then you β-decay, right? You go here, and then you β-decay. For instance, the R process is all here on this side, on the right side of the nuclear shard, right? So all that rapid neutron capture will come down to the value of stability. Everything will come down eventually by β-decay to produce those elements that we see around us. For instance, here you can see that Xeno-134 and Xeno-136, they will block that β-decay. They will block the possibility to create barium-134, and you can see that barium-134 is quite has a very little abundance. And also it will stop producing barium-136. There's no another xenon heavier here. Xeno-138 is not unstable, so barium-138 will be produced much easier from the R process, right? Also will be produced from the S process, right? There will be elements which are produced by both, and some elements which cannot be produced by the R process simply because they are blocked by other stable nucleus, and this stable nucleus cannot β-decay to another stable nucleus, right? So this matter being released by the S process is quite huge, and we have this new satellite, the Gaia satellite from the European Space Agency, which is making a 3D picture of the universe, of our galaxy. And in the process, you just take some snapshots of what's happening on some of the AGB stars, and we see here the turbulence, the dynamics of these turbulences on the surface of AGB stars, and how these elements are ejected to the outer universe, and they enrich the different gases and nebula, and so elements and new stars can be created, right? So there are different weak, main, strong S processes depending on the neutron exposure, how many neutrons you have. But this is quite understood, the slow neutron process. What is not so clear is this rapid neutron process, because what we infer, I will mention it later, is we know what is the S process. So let's look at the abundance of elements in our universe. So whatever is missing from the S process must be the R process, right? So this is how the R process infer, and this is why there are so much of discrepancy. It's like, dark matter, the rest must be dark energy. It's our ignorance of the situation what allows us to say such thing, which may be right or may be wrong, but we don't know for certain. So abundance of elements. So again, as I was mentioning before, this the S process, the R process, and the R process is determined by the remaining from whatever the S process we see. Let me see. Here we go. So the R process, I will also outline that this later, is coming. You know, we have elements being created in the merging of two neutron stars, and these ratios of elemental abundances, they are very interesting because depending on that ratio, we can look at the different stars, AGB stars in globular clusters, and they will see that the ratio depends. You know, if you have a ratio of strontium to barium between -0.5 and -0.4, and this is the log, and normally they are related, the abundances, to iron, but in this case you can also check different ratios, and if this is the ratio in particular, you have R process. If there's a different ratio, here is the definition of that ratio in this at the bottom here. If you have less or equal to -1, then is the S process what is supposed to be the main source of that particular star, right? So this is how we infer by looking at the abundance ratios that we see in different stars, whether the R process or the S process dominate those kind of stars. The metal poor stars, I mentioned it here, but I'm going to talk about those later. They're supposed to be those stars which still remain out there after the first big supernovas. But then let's go to the rapid neutron capture process or rapid process, where we have lots of neutrons being created by this huge explosion, supernova, or as we know now, the astrophysical side is most likely the neutron star mergers, and most of the elements, half of all elements beyond iron, that are produced by the R process. The other half is produced by the S process. And obviously the R process is the only source of elements beyond lead and bismuth, because there's a gap of unstable nuclei, and then you cannot reach from lead and bismuth to the next one through the neutron capture. So any elements beyond stable elements, beyond lead and bismuth, like the uranium, thorium, they have to be produced by the R process. So as you can see here, very importantly, is that we have a huge variation of different drip lines, you know, depending on the model, depending on the effective interaction, depending on the different density functional theory, whatever, you know, you have different possibilities for that R process path and for the drip line, which is the line of stability before a nucleus becomes unstable and emits a particle, right? Before a nucleus can be formed, and the predictions for the neutron drip line and for the R process path involving heavy neutron-rich nuclei exhibit a significant variation due to a wide range of conditions not accurately determined, not accurately measured in accelerators, and there's a lot of millions and millions of dollars actually towards building these facilities where we can reach far away into the neutron drip line, that terra incognita that people we all want to investigate, right? So here, for many years, we have discussed about what is the astrophysical side of the R process. It wasn't clear at all. Supernova, some people mentioned collapsars or neutron mergers, where neutron star mergers were many years ago were an option. Although because of the time scale, they were never considered very heavily as a real option, because you know, to get a neutron star, first it needs time, and then to get them merged takes more time. So according to the cosmological time scales, it wasn't very clear that the neutron star mergers could be. But we saw the LIGO experiment, and then afterwards our telescope SALT and all telescopes around the world, they saw the ejecta of the kilonova in 2015, and they discovered they figure out, despite the fact that there's no real absorption lines, but this simulation, it looks like there's a blue shift for a line which should be strontium 2, an absorption line which should be strontium 2, but because it's blue shifted, it moved to the left in the wavelength here, and you can see this dent, which it is predicted to be that line in strontium 2, right? The electron line. So here we have the black body radiation, and all these dents are obviously absorption lines which happen on the surface of elements, or in this case in the ejecta after the kilonova. So again, there's no clear experimental. I want to be always very clear with what we know and what we don't know. There's no clear experimental evidence. There's a dent here which may correspond to this blue shifted line from strontium 2. And obviously, this was the first evidence to say, look, this ejecta from this kilonova was published in Nature, is producing heavy elements, and neutron star mergers are likely a source of heavy elements through the arc process. So let's go back to the metal poor stars and understand a little bit of the universality, what we are talking about. That's the title of this talk. So if we go back to observational nuclear astrophysics or astronomy, we know that there was a Big Bang, then there was this primordial gas, and we have lots of big stars being created. Those are the big population 3. I don't really know why they call it population 3 instead of population 1 or whatever. I don't know, but that's an astronomy thing. So this big supernova exploded quite fast because they have lots of, they were massive and they have to fuel, they have to burn a lot to keep shining. They produce lots of elements, and those elements produce the population 2 stars, right? These are the ones we're interested in. These guys are still out there, some of them. The population is very small, less than 0.1% of the stars that we see around us. And afterwards, obviously, we have other kind of supernova, more are processed. We have stars like our sun, which is a feeder of different processes, different stars, different supernova which were here before our sun, and that's why we have a lot of elements that we can see on the surface of the sun, or also on the surface of the Earth. So layers of chemical evolution are difficult to disentangle. So these metal poor stars, they provide this testing ground because they're the simplest case scenario. So with the new era of high energy resolution spectroscopy that we have, different telescopes of different satellites, the Subaru, or here at SALT, we also have the high resolution spectrograph in South Africa. This is one of the beautiful things of South Africa, that you can have, you can run an experiment on nuclear physics with the largest accelerator in the southern hemisphere, or you can go. I'm here in half an hour from ITEMA labs, and just 5 hours drive to Sutherland to SALT and get some data for some of these metal poor stars, for instance, right? And as you can see, the big difference between the sun with lots of lines after many generations of things happening, and here we have the typical metal poor stars of abundances of -3.2, where you have the iron, the nickel lines, the iron lines, and you have here another metal poor star, which at that time was the most metal poor star ever being discovered by Anna Frebel and by Aoki. And as you can see, the simplicity is greater. So if you don't understand something, the best, you go always to the simplest case scenario, and this is how you learn. And as you can see, sometimes you see these strontium lines in these metal poor stars, and then you don't understand why. And then you investigate, the different ratio, the different abundance ratios, and you see, wow, these guys actually were fed by this population 2 big supernovas, and then you know that these are processes happening in those metal poor stars, right? So it's a abundance problem that you can investigate, and the best testing ground is presented by metal poor stars. So actually we have a project at SALT. I'm just not telling you, we just do it. And we have a project with the high resolution spectroscopy at SALT with HRS, and we use they gave us high resolution data and medium resolution data that we analyzed, and we have been working with that data. Actually, my student Blaine was working with this data, and we did some with help from the big astronomers, from Dave Kilkenny, Enrico Olivier, who was here before, and then Tony Linus-Gray, who was a College London in the UK. He's an expert on metallicity of stars, on the atmospheric corrections that come into these simulations here, into these MOOC simulations, and the simulations are so beautiful that they can actually tell you more. Once you feed the data to the simulation, it can tell you what is the surface gravity, what is the effective temperature, what is the metallicity relative to the sun, So we found actually a metal poor star. Our first, it was the star that we studied, EC 2029-1 3603, and this refers to the declination and longitude of the star within the Edinburgh Cape Blue Object Survey, which was published by David Kilkenny, who is an astronomer at UWC and is one of those very wise astronomers who know about this UV light, B minus V, and how these guys on top here, they may be well candidates for metal poor stars, basically because the ultraviolet is suppressed. The left side of the black body radiation is suppressed, and then we can see some of the lines, or the absorption lines, which have less wavelength. So we saw those, and then we presented this work in some conferences in Brazil and here in South Africa, but we haven't finalized this. We haven't published this. This is our metallicity, and it will be nice to finish this work. But we'll see whether we can finish this. And once we finish this, we have a pipeline to develop this kind of work here in South Africa by South African scientists. So what's universal about all of this is that, in the simplest case scenario, you agree with your abundances. You are in the good space with physics. As you can see here, there was a paper in 2008 by Christopher Sneden, John Cowan, and Roberto Galino, and they combined. They just shifted a little bit on the y-axis the different curves. The blue curve is the abundance, the R process abundance in our sun, and the red dots are the corresponding to different kind of stars, right? And as you can see, they match beautifully the abundance pattern that we see now in our sun. We just shifted so you can see the different stars, how they agree with the sun abundances, right? So this comparison of neutron capture abundances in these 6 stars, it was the strong indication that the abundance patterns of the heavy stable elements from barium through lead in the most metal poor stars are consistent with the scale or relative solar system R process abundance pattern, right? And this was a beautiful picture, which was confirmed a little bit later with more data, 10 years later, by Anna Frebel and Kajino. So here is a picture from Anna Frebel's review article, where elemental abundances of metal poor stars in the galactic halo exhibit the same elemental R abundance, R process abundance pattern as known from the solar system abundances. This pattern appears to be rather universal, right? This is the term of universality that we are trying to investigate. This fact suggests a rather well-defined origin of heavy elements beyond iron, We do not know if this may be only an artifact of nuclear properties, such as binding energies and beta-decay rates, or it may be point to a single cosmic site with astrophysical conditions that are generated uniformly throughout cosmic time. So obviously, there's a very important question mark here on how these elements are produced. We know that everything matches, the abundance pattern, everything looks universal. But what is the reason for this universality is the purpose of this talk. So now let's go back to our nuclear physics. In that sense, we go back to what we know. We're going to combine the nuclear physics with what we know in astronomy. Investigate whether there's we know there must be a macro connection. And is there both a universal nuclear and cosmic pattern in the creation of heavy elements beyond iron? So this is the question we're going to try to answer, because it wasn't clear from these articles. Obviously, it's not clear that, okay, we have a universal pattern. Why? There must be a reason for this, right? So, and then we go to Arkady Migdal, who was a Russian scientist, very well known for all his work and for his school. And he combined the hydrodynamic model with second-order perturbation theory to determine the nuclear polarizability. He determined it from two different points, right? So in such a way that you assume that you have interpenetrating fluids of protons and neutrons, where you have a potential given by the Coulomb force in the protons, and this allows for this interpenetrating fluids. And you can see here the semi-empirical mass formula. Now we have moved from neutron and protons to a density for neutron and density for protons, and instead of A, we have the density for the system, total density. We assume there was a radius of a nucleus. The nucleus was spherical. Basically, he assumed it was kind of a Steinwalder-Jensen model, where you have protons and neutrons in a sphere moving around out of phase, right, in a fixed sphere. And by doing that, he concluded that the sigma minus 2, which is defined here, the total photoabsorption cross-section, divided by the energy of the gamma square, integrated between 0 to infinity. Obviously, this is not possible, but as low as possible, which is normally the neutron threshold, and as high as possible, which is normally the pion production. And he concluded that by combining these two formula and assuming a constant value for the symmetry energy, he got 2.25 a to the 5/3. This power law formula was confirmed by Levinger in 1957 with the available data, and then afterwards with much more data, with the atlas of photoneutron cross-section, was confirmed by myself. Actually, I got 2.38. Levinger got 3.5, so even closer, many years later, almost 70 years later, after Levinger published this remarkable paper, right? So, 75th anniversary of Migdal, we celebrated at the Taste of Nuclear Physics last year, and this paper on quadrupole and dipole gamma emission from nuclei, which was the first one where a collective motion, the giant dipole resonance, was predicted and soon later discovered in Caltech. So there was a paper on the 50th celebration by Danos and Ishkanov, other authors here, and there's another paper. I found this recently, 2021, celebrating the 75th anniversary of that particular paper, which was a milestone in nuclear physics. So it's another beautiful paper. Danos and Ishkanov is still there, right? Yeah, Ishkanov is still there. I think Kapitanov is not there, but it's probably a new. He will remain for the 100th anniversary, and hopefully we can contribute more in between to try to understand this fascinating field much better. So here we go. And then we have the symmetry energy that at that time Migdal assumed as a constant. We know it's not a constant. Depends on the mass number of the nucleus, the number of protons and neutrons. And as you can see, alpha and alpha here, they can be combined together. And this sigma minus 2 value can be related to the symmetry energy. And the symmetry energy, again, we go back to the beginning, to my Oxford times, where I gave that talk. And that, and you know, we link it to the binding energy here. So now we see that this is sigma minus 2 that we have in this equation. We can determine that from data. We have the total photoabsorption cross-section, which normally consider photoproton, gamma protons, gamma neutrons, you know, all the different reactions which involve proton and neutrons. And we see that there's a polarizability enhancement of loosely bound nuclei. As the nuclei become loosely bound, there seems to be an enhancement of light of a nuclear polarizability of sigma minus 2, or the symmetry energy is reduced, right? Either way, because they're inversely proportional to one each other, right? Sigma minus 2, and here is the denominator, and here is in the numerator. You can equal these two terms, right? So then we'll get sigma minus 2, and again we could reproduce with a formula which was quite nicely here. Once we included that the mass dependency on Migdal's equations, it was clear that there was an upbend here for light nuclei. But not only that, we kept investigating the situation, and we look at the data. It was for the first time that we saw a dip at particular magic numbers. You know that magic numbers are those where nuclei are particularly stable, because there's a shell which is being full, right? It's full with protons or with neutrons. In this case, for neutron shells being full for this magic energy, where there's an energy gap for the neutron to be populated to the next level, right, to the next single particle orbit. So these magic numbers, as you can see here, they have in N126, N82, N50 here, and in this case N28. And you know, we have different. This is the low energy enhancement of the without and with low energy enhancement, which is also making a difference, but we cannot go into the specifics now. But as you can see, this was a beautiful discovery to see that there are dips of the nuclear polarizability at those particular magic numbers. So obviously the situation implied that the sigma minus 2 values were sensitive measures of the long range correlation of the nuclear force, right? So then we go and try to fit the data on the different, compare with different calculations also. So we have the data, and we have different possibilities for this enhancement of light nuclei. And as you know, the symmetry energy parameters, the surface and the volume, are closely related to the equation of state of neutron stars. So it has a big consequences. And it was at that time I did a review article on these proceedings. So the 4th South Africa Joint Institute of Nuclear Research Symposium in Dubna 6 years ago, and we wrote a beautiful paper with all the possibilities given by theory and given by data. And also we published something similar in a review article here, which was published last year. And again, these features assigned, assuming the Bring-Axel hypothesis, which we're going to mention in a little bit. These features assign the nuclear dipole polarizability as a sensitive measure of the long-range correlations of the nuclear force, and provide a new spectroscopic proof to investigate collective phenomena, shell closures, and the elusive nuclear symmetry energy. Okay, so this paper was actually one of the most read articles last year, and it was selected as one of those 30-some papers, articles where they were selected as a collection of articles of long-standing value and importance in their fields, which was very nice to see. So now we look and we see the symmetry energy from different points of view. So here we see the symmetry energy extracted from binding energies. And you can see that there's a convergence converging to 23 MeV, where this red curve comes from the leptodermus approximation. And this is normally, there are different approximations, but this one is the one which has a better fit to the masses of isobaric nuclei, and is the one which is commonly used. As you can see, the symmetry energy converges by different methods, which we're going to quickly explore at 23, 27 MeV for heavy nuclei. So then our students, our Manus students in 2019, they also explored the possibility of extracting the symmetry energy. As I mentioned before, the symmetry energy is inversely proportional to the sigma minus 2, or vice versa. And from that, getting sigma minus 2, we could, from the available photoabsorption cross-section, gamma P reactions, gamma N reactions from the X4 database. So they got all these data points. I think they have one with the uncertainties are very small, 10, 15%. But there's some discrepancy, as you can see here. And obviously data, there's not much of gamma P data available because the important thing in those years were the gamma N, were to know how was the power of this nuclear bomb. So there's a lot of gamma N data, but there's not much of gamma P. So gamma P is what we need to get our hands on. Even the gamma N data were not analyzed 100%, as we know now. And there's a new compilation of all this data that has to be explored as well. So basically, in this case, as you can see, the symmetry energy, there's a variety of points, most here and there, but it goes to about 26 MeV. So there are different methods, and they all agree with that 23 to 26. So then we went to the actual giant dipole resonances, and which is, I haven't defined the giant dipole resonance, but it's the most absorption and most emission of gamma of photons comes from the giant dipole resonance. So whenever there's a absorption of radiation, it's emitted or absorbed by the GDR. And this is the information, most information comes from photo absorption of chunks of material, particular isotope, which is enriched, and say, okay, lead-2A, let's enrich lead-2A, let's scatter it, and with photons, let's use some bremsstrahlung or different techniques like positron emission, and then positron annihilation, and then let's investigate the giant dipole resonance and that emission from these different nuclei. Also, it tells us how elements disintegrate into something else. The gamma N will lead-2A, the gamma N will disintegrate into lead-207, or gamma P will go into bismuth-207, right? So this is very important information, as you can imagine. And it was parameterized here by Danos, who actually took the SJ model, the Steinwelder. I mean, Klaus has to tell me how to pronounce that name. Steinwelder-Jensen model. And he just included the width of the giant dipole resonance, the width of the resonance, and with this equation, assuming also that we have an average centroid energy and the full width of the total Lorentzian, we also did for the same thing for the 4 nuclei. We integrated, we took the data from X4, integrated, and see what is going to be the symmetry energy according to this equation here, right? And so we see now that these converge around 26, you know, and these are the parameters. These are the parameters for that leptodermus approximation. And these are the ground state built, you know, the GDRs built on ground states. We are talking about the temperature, which is about zero MeV, right? I want to tell you this because this is not the temperature that we normally see in those astrophysical environments, right? Most of the information that we know, they come from these GDRs, giant dipole resonances built on ground states, which are not really what we need. So again, we apply our method because assuming that there's a Brink-Axel hypothesis, a GDR can be built on every state in a nucleus, we can have GDRs built on excited states, which may be more closer to our astrophysical environment, right? So these excited state GDRs present at least for moderate average temperatures, less than about T equal 1 MeV, and spins, there's a critical value for the total angular momentum of the states, similar centroid energies and resonance strength relative to the Thomas Reike-Kuhn or the TRK dipole sum rule are those found for the ground state counterparts. This is a formula which can be found in many different fields, the 60 N Z divided by A 1 plus delta, where delta is the resonance factor. And these similar features indicate a common physical origin for all GDRs, right? This was the assumption, and this Brink-Axel hypothesis has been confirmed quite closely in different experiments of the low energy enhancement by the Oslo group, and you know, it seems to be holding nicely. So we investigated what happens for those GDRs built on excited states, right? And we have different GDRs here, which again, they follow and they have similar, but not the same energy centroids and width. And in fact, as you increase the temperature, as you go up in excitation energy, the width starts broadening, and this is another effect. It's called the Landau damping effect. We're going to go through that in a little bit. But basically, we apply the same method as for T equals 0 MeV, GDRs, and we collected the data available, which is not much, on GDRs built on excited states. This is for technetium 97. And a curiosity, we figured out, you know, that different temperatures are different from 0.7 to 1.3 MeV, and this is important to mention right now because this temperature is not the temperature of real interest in the astrophysical conditions of neutron capture on the R process. But we have a similar constant behavior which goes from 0.7 to 1.3, right, for different elements. So the symmetry energy doesn't seem to change between 0.7 and 1.3. But the important point comes here, right? So now the symmetry energy for these excited states, which are more closer to the astrophysical scenario that we are investigating, to the neutron star mergers or supernova explosions, you know. So we have a totally different behavior, as you can see, compared to the ground state of nuclei. There's lots of information here, very little here. This is all the information that we collected, including the form spherical nuclei. These are the data points, but you can see that there's a different trend. There's a different trend which tells you that for heavy nuclei, the trend converges here for 26, 27 MeV, as we mentioned before, for ground states. But here we go up to 31 MeV. Actually, 31 MeV. So it's much higher. This is the error bars and the uncertainties for heavy nuclei, which is where the R process is more dominant. We see an entirely different trend than we see for this red curve is the same as this red curve here, right? So we see that something is happening at these temperatures, which are closer to the astrophysical temperatures. So, and this I will we can explore quickly. We can explore quickly. How long? I have 5 more minutes. So we can take from the textbook 23.7 symmetry energy. This is the parameters of the semi-empirical mass formula. So if we just let me just Control XS and then this Python. Whoa. You can see the 2020 mass. Let me quickly show you nicely. You can see, for instance, that we have perfect match with those parameters when we compare to the atomic mass evaluation 2020, right? This is a semi-empirical mass formula, the bluish line, as compared to the masses, right? To the what is the binding energy per nucleon given by the experimental masses, right? 2020 evaluation. So if we go here, just for the heck of it, let's go to 31. And there's to Control XS. All right. As you can see, there's a huge reduction, in this case, of the binding energy, right? The same thing happens if, obviously, if we look at the this is the nuclear chart, and here 30 MeV, 23.7. As you can see, there's a much wider, the neutron drip line is much wider than for the particular case of 30 MeV. So basically, the nuclear chart starts closing in. Let me see if I have those here. Yeah. Go through this one. Let's see. Want to see here what is the 23.7? Here we go. Let's put here 23.7 and Python 3 chart 3 PA. And here we go. You see what happened with the nuclear chart. Those are all the elements. The yellowish here, the white ones are the more stable ones, that line of stability. But we change that to 31. We see that now the whole thing again closing. There's a closing. You see, maybe not so clear here, but you can see that basically the nuclear chart or the drip lines are closing in particular the Newton drip line, right? And this is the effect of having a smaller, a reduced binding energy. So then we are almost there. Now we can explore what happened at high temperatures, but we don't care because the high temperatures are not really our case, our astrophysical scenario. But we see that this was predicted a long time ago, in 2003, by Gorielli, and when he did some microscopic versus macroscopic calculations, and he could see that there was a sudden drop on the reaction rates for those particular heavy nuclei which were involved in the ARP process, right? So he concluded that all ARP abundance calculations performed so far were wrong. And not only that, he also mentioned about the so-called universality of the ARP process abundances, as inferred from the observation of ultra metal poor stars could possibly be explained by the rapid drop of the neutron capture rates at increasing neutron excesses, right? This means that you cannot go so far by capturing a neutron, but you quickly go to the line of stability by beta decay, right? By beta minus. So then let me actually just to finish a little bit of the cauldrons in the cosmos. This is a beautiful book, but this is what happened. You have a kilonova, which is like 10 to the 11 Kelvin, 8 MeV Kelvin, 8 MeV, sorry, temperature, which is very high. At that time, there's a kilonova, there's an ejecta, and there's gamma ray burst, there are quarks, gluons, then eventually you combine protons and neutrons. You know, this is a typical scenario as the temperature comes down and we are creating matter, right? So then what in our region, and that 0.05% of abundances in our universe, we are interested now at when the temperature goes to 1 MeV, drops to 1 MeV, which is about 10 to the 10 Kelvin. So these are likely the temperatures where seed elements are created before charge reactions freeze out, before the charge, the proton number is, the Coulomb barrier is too large and you're going to produce more. And basically, then you reach the limit of 0.5 MeV, less than 0.5 MeV, where actually neutron capture may start occurring until the point where you have a few 10 to the 8 Kelvin and you reach basically the temperature of T equals 0 MeV, where neutrons are finally consumed, and that's it. That's the end of the neutron mergers, the end of the kilonova. Everything has been created, and then in this ejecta you can see what happened in the process. You know. So what happens actually when we go down to T equals 0.5 MeV? We don't know. We don't know what we know is that the temperature remains constant, and we don't know for how long or how low the temperature will remain constant. It remains constant from 0.7 to 1.3. If this is the case, then what we will see is that there's a narrowing down, closing of the neutron drip lines, and a closing of different possibilities of this exotic R process path, which produce the elements beyond iron, right? So with that, we also did some reaction rate calculations, and we calculated either using Tallis or Empire. We predicted a reduction of 100 for nuclei with mass 200. And we can see here the reduction in the neutron drip line from a symmetry energy of 23.7 MeV to 30 MeV. And all of this was submitted for publication to Physics Letters B. We titled it, these are my collaborators who are experts on GDRs and some of our students, Sewan Wetseni, Brendan Lesh, and Dile Zulu. They are the remaining of those minor students who were originally in this task of investigating how elements are created. But the conclusions here as that symmetry energy shows at T equals 0, actually we'll say T.7 and 1 MeV, shows that there is a clear closing in neutron drip line, which constrains the up process flow and narrows down the nucleosynthesis of elements, hence supporting the universal pattern of R process abundances observed in galactic halo nuclei. Not only star mergers can be nurseries of R process elements, because everything is happening at the same temperature, and those supernova, collapsars, whatever other stellar explosions are there, they can also produce this. They have enough neutrons to do so. And we must explore what happens at temperatures less than 0.5 MeV. And actually, I didn't put a slide there, which was quite important. But for that, I will go to our webpage, nuclear, and I will just go here. Actually, that's the other webpage. And we see here GAMCA, which has been commissioned. We have all the detectors. We have been, after 9 years, everything is ready. And there's a possibility to study what happens at temperatures of 0.5 MeV, at those actual temperatures where neutron capture starts happening, right? And to investigate the symmetry energy of GDRs built on excited states at that particular temperatures of less than 0.5 MeV with the current facilities that we have here in South Africa with Gamka at Itemba Labs. Okay, and I want to finish with Monday starts on Saturday. Their motto was Monday starts on Saturday, and they had accepted as a working hypothesis that happiness lies in the constant cognition of the unknown, which is also the meaning of life. I recommend this book to those who want to be physicists, and to those who are physicists. If they haven't read it, also I recommend it. Thank you very much for your attention.
Yeah, Nico, thank you very much for an excellent and very active talk, including book recommendations. Very nice. Thank you very much.
I'm sure Ilya has read this book.
I'm sure. I don't know.
Of course.
No, I didn't.
Of course.
Yes.
Of course.
Okay. I didn't. Yeah. Okay. So I will be busy this weekend. Yeah.
You need to.
Are there any questions for Nico? And please, since we're not so many, you're most than welcome to raise your hand, and we will give you the right to speak. Here we go. First question is, Ilya already sorted it out. Ilya, sorry, I'm stealing your job. Yeah.
Klaus, yeah, you
Hello,
want
yes.
to ask a question.
Yeah, question and comment. Can you hear me? Yes.
Yes.
Yeah, first of all, thanks. That was a deep insight, Nico. And the question would be, you speak about these temperatures. How is it then defined in this experiment? Is it the Q value, the remnant after the reaction?
Right. The temperatures, these generally, you want to let me tell you, this is what you do. I want to show you the PLB paper here. So you try to constrain your reaction so it doesn't what is it? Here, no, not here. So basically, you have your cutoff on temperature. It depends on the Q value, but also depends on the energy, of the GDR energy. But what you try to do always, let me see, angular. Here we go. You see that you have a critical angular momentum, which is well known to be such, and the temperature, critical temperature, which is supposed to be such. And this, the best example are those experiments where you use alpha scattering, right? Alpha scattering, alpha prime, alpha inelastic scattering. It doesn't allow you to go very high in angular momentum. So this is our best task, our best goal to determine GDRs which are built on, at those 0.5 MeV or less. That's our hope. But the GDRs, built on excited states, there's very little information, and this is how you always try to go after. The reaction must be such that the temperatures, normally they use cascade or the different evaporation model calculations to determine, first before we run the experiments, to determine what is the temperature of the system, right? And what is the energy of the GDR, or the compound nucleus reaction, that you're going to use.
Yeah. So, and then this table you showed with this view on, this is on real excited states with this 10 values.
Which table?
The one where you derive this other. This one.
Up there?
Yeah.
This one.
No, yeah, this one.
This one, yeah. So this is just a plot for the different temperatures, and this is a factor F, which I think is related to the different angular momentum, also the average. But these are different temperatures at different MeV, and these are the temperatures that we see here, actually. Those are the temperatures that we see in our, the corresponding temperatures are here, right? In MeV,
Yes.
I mean, temperature.
That's from the formula again.
That's from the formula. From the formula here, we feed the data. I mean, we feed with the formula the data and look at the energy here, the EGDR, at the width, and from there we get the extract the symmetry energy, right? So these are the data points, and this is the fitting to those data points as we did for the GDRs built on ground states here, right?
Yes. Yeah.
So the only difference, yeah, is that we use here also we have a few deformed nuclei that we wanted to fit, and we just use the average centered energy with the total full width for the full Lorentzian, right?
Yeah. Yeah, just the other comment then, I mean, for all of that, I remember when I did this one paper with the laser, there was around 40 to 50 gamma P cross sections known, and a lot of them were just only the integral cross sections. So they have been very neglected because they're also harder to measure. But coming from ELA-MP with the gamma beam, this will be a playing field for such experiments for the right ones. So as long as you have the right targets, they don't have to be that ultra thick. There could be a lot of progress made in there. Maybe another interesting thing, this gamma beam can also be joined together with the laser pulse, where you have a tremendous real plasma to start with at some stage, and tremendously high intensities. That is probably
that is a possibility, Klaus, because also we could do gamma prime, right, and see which will be a better, we'll fine tune the temperature even better than with using alpha prime.
Oh yeah, I mean that is will be very good. Tunability is up to 19.5 MeV and goes down to 200 keV.
Yeah.
But it will be a long experiment because the tuning takes its time. But yeah, for that it would be ideal, and certainly a lot of findings to be done with a system like that.
So to the audience, we have to say that we are setting up a collaboration with your facility in Romania.
Yeah.
Hopefully, we just submitted a paper, a very nice one, just to around these studies of gamma N and gamma P competition, because as I said before, we don't know much of the gamma P because everything was
yes.
Right.
Thanks.
But did you understand things? It was clear enough or not? I hope so. I see Rob Allen is here.
And Rob have a comment. Yeah,
I just put in a comment there, so as not to take anyone's time. But no, great talk, Nico, and it's really nice to see the elegant way in which you're investigating the symmetry term. But just to comment, years ago when I taught the semi-empirical mass formula at honors level, I used to add the gravitational energy term to the formula and then ask the students to work out the minimum mass of a neutron star. And you can do that because as you take the limit as A goes to infinity, you see it's a fight between the asymmetry term and the gravitational term. The gravitational term wants to keep the star together, and the asymmetry term wants to blow it apart. And so, if the neutron star loses mass in a collision or whatever, it blows up. Or it has to. Anyway, the answer you get is a bit too small, but that's not surprising that the SEMF doesn't quite fit. Because
this is very important, Rob, for SKA, to combine this information, and the symmetry energy is related to that neutron star. What is the radius of the neutron star, right? So there's a lot of synergy between this and SKA, right?
Definitely, yeah. It's a connection with the nuclear physics and astrophysics.
Thank you, Rob. I actually wanted to say one thing. I haven't finished the story in Oxford. So I was in Oxford and I forgot my backpack, so I came inside and the jury they were deliberating about who was going to be the winner of the students, of the young physicists who went to Oxford. The winner of the talk, the best talk, will give a presentation in an international conference in Hungary. So I arrived there they didn't notice me, so I went to pick up my backpack and I was leaving. As I was leaving, one of the juries, or the people there, who was the one who asked me about the semi-empirical mass formula, he said, well, we cannot give him the prize because he didn't answer the question on the semi-empirical formula. So obviously, so I hear that, I say, wow, I just lost the prize for not answering that question. So the prize was to another very good talk by an English fellow, and he was the one who went to, I came second, but that was the point. And 20 years ago, I didn't know much about where to use this empirical mass formula, and now we see that it is actually explaining so many things.
No, it's an amazingly useful tool just to get to grips with the basic understanding of the physics underlying nuclei.
Thank you.
Thank you, Rob. Thank you for your comment.
Yeah, no,
thank you for being here.
Get homesick for nuclear physics sometimes.
Actually, you were in Dubna last time when I was also in Dubna, remember?
Yeah, very well.
We were there together.
Yeah.
Excellent.
I see the thank you, Klaus. I just see the chat.
Yeah, Nico, it doesn't seem that we have further urgent questions. Yeah, so before I thank you, I just wanted to remind the participants that are still with us that Nico agreed to a short social event, yeah, where you're welcome to chat to him or among yourselves. I've posted the link in the chat. Yeah, it's called kumospace.com/nitex_social. Yeah, and as soon as we finish here, we will move to the pub in the social event. Yeah, there will also be drinks served. Yeah, just follow the link. Just follow the link and get surprised. Yeah. Okay, Nico, thank you so much. To you, thank you, Ilya, for moderating the questions. Thank you. To the participants for being so faithful to our NITEX colloquium. And I'm looking forward to see some of you maybe at the social, or otherwise next week on Monday we will be here again. Thank you very much. Have a good afternoon and evening. Thank you. Thank you, Nico. Thank you so much.